The Langmuir Lecture is always one of the keynote events, in fact, the keynote event of the conference. I will say that the year I joined EIS in 1990, Bill Fagey gave the Langmuir Lecture, and I was able to assess whether or not I wanted, as an incoming officer, to work with various supervisors based on what their reaction to his address was. The Langmuir Lecture honors a person who's made significant contributions to the fields of epidemiology and public health. As you know, I think, it's named in the honor of Alex Langmuir, the longtime head of the Epi Division, someone who had the foresight to realize that a sleepy little publication coming out of Washington, D.C. called the MMWR could become a major vehicle for CDC to communicate with the country and the world. The foresight also to create the EIS program. We owe a lot to Dr. Langmuir for what CDC is today. Now, if I can see a show of hands, if you could just raise your hand and leave it up. How many people here have used the software package EpiInfo? All right. And now, you can put them down, I guess. How many people have used Google? How many people have used neither? How many people are embarrassed to raise their hands? Well, this year's Langmuir Lecture honoree is Dr. Jeff Dean, who has taken a very different road from many of us here, but he's contributed to public health in very important ways. He's currently Google Senior Fellow in the Systems and Infrastructure Group, and he'll speak about large-scale machine learning and its application to public health. Now, some of you may wonder what Google has to do with CDC and EIS. I think there are actually some similarities besides the role that Jeff Dean has played in both of them. I think we're very productive when we're informal, creative, irreverent, thoughtful, think big. And I would say that at CDC we try to aim a little higher than do no evil. But Jeff, as some of you know, while still in high school, worked with his father, Dr. Andy Dean, EIS 74, on some of the early programming for EpiInfo, CDC's key data analysis collection program that is now used around the world. He earned his bachelor's degree, summa cum laude, from University of Minnesota in computer science and economics, and his PhD in computer science from the University of Washington. Before graduate school, he worked with WHO's global program on AIDS, and he also designed a lot of statistical software for modeling and forecasting. He was elected to the National Academy of Engineering in 2009, recognizing his work on the science and engineering of large-scale distributed computer systems. Jeff has always been passionate about getting computer systems to work faster. Much of the near instantaneous speed of Google is the result, directly or indirectly, of Jeff's work. He's working on stuff now that I think will astound us when it gets released in the future. I will say that when we talk in the CDC world about EpiInfo and Jeff Dean, he's a legend. If you talk, however, in the computer world about Jeff Dean and optimization of things like searches, he's also a legend. So it isn't often that people can be a legend in two different worlds, even if those worlds do intersect in important ways. I'm particularly interested in learning about how Jeff's work can translate into ways we can use IT to improve our impact in this country and around the world. Last year, I spoke with Jeff about some possible areas to work together on, and I was very proud of the fact that in one of our programs, the Million Hearts program, and a pilot project, we've been able to get feedback to clinicians on a 1-month basis. So actually you could get feedback on how you're doing. You didn't have to wait a whole year. You waited about a month. And Jeff said, well, we try for a feedback loop of about 39 seconds. And I thought, we have a long way to go. So please join me in welcoming Dr. Jeff Dean back to CDC.
Okay. Thank you very much for having me. Thanks, Dr. Frieden, for inviting me. I'm very excited to be back here. I've kind of taken a meandering route, as you said, but what I hope to do today is to talk about the sort of large-scale infrastructure and data processing techniques that we use at Google, because I think there are a lot of similarities between the kinds of processing we want to do and the kinds of processing you'd like to do on public health data to improve public health. And so I'm going to talk about things that are not necessarily directly public health problems, but if you squint at them just right, I'm hoping you can imagine similar problems in public health that you face in your day-to-day jobs. So, there it is in computing in 1980, a beautiful looking computer with dual floppy disks, EpiInfo, which I found on Google image search. And that was kind of the world about 20 years ago. You know, you would get your data, you would store it and process it on a single computer. What changed about 15 years ago is we had the internet, we have now large-scale data centers. So Google as a company started as a research project at Stanford. So our two founders, Larry and Sergey, were grad students at Stanford, and they were interested in processing the web pages and building information retrieval systems. But their mean advisors would not really buy them enough computers. So the way they got computers was they would volunteer to set up other research groups' computers, so they would go down to the loading dock and kind of intercept them and then set them up. And so they ended up with more computers than just one, which is kind of good. It was kind of a hodgepodge mash of different kinds of machines, because each research group would order different kinds of machines. But that's kind of how Google got started, is the ability to take more than a single machine's worth of processing and apply it to large-scale problems. So when Google was a company, we knew that that was what we wanted from the very early days, was to be able to apply as much computation as we could possibly afford to large-scale computation problems. The way you can run more sophisticated algorithms and more interesting kinds of computations is by having lots of computational power. And one way to do that is you can go to a really high-end computer vendor and say, give me the biggest possible computer you'll sell me for like $1 gazillion, and they'll be happy to do that. But at some point, you would exhaust even the capabilities of that single machine. So you really need many, many computers. And at that point, rather than having a handful of really high-end sort of server-class machines, you'd rather have a bunch of crummy machines, because you get way more computing power per dollar by doing that. So we decided we would not even buy machines, we would buy components and assemble them ourselves. And so this is what we affectionately referred to as the Cork Boards. So we had 4 motherboards and 8 disks, two disks per machine, and a single power supply for all 4 machines, which turned out maybe not to be such a great idea. And then you probably can't see it, but there's a thin layer of cork insulating the machines from the cookie trays that they sat on. So that was kind of the origins of Google's processing, but we had thousands of these machines deployed, and they worked pretty well, and they let us use a lot of computational power to provide search. If we go forward a bit, this is the next design. At that time, we were not building our own data centers, but we would lease space in large data centers, so you get kind of a cage worth of space, and you could sort of put your machines in there, and other companies were in there putting their machines in different cages. Curiously, this was kind of during the height of the initial .com era, and so data centers were getting built out really quickly, so all these different e-janitorial supplies .com companies could start up. And the data center providers were also coming up and were kind of newly evolving businesses, and they actually didn't charge you for power, which was kind of nice. They charged you by the square foot. And so we had an incredible incentive to pack as many machines in as we possibly could. And they actually ended up needing a little help with their cooling, and they had to leave 5 cages around us empty because we were consuming so much power. As a consequence, we got incredibly good at moving out of bankrupt data centers and into new ones. So there's a cage, you can see it unpopulated, and then 3 days later, we're able to wheel in these racks. We sort of pre-wire every rack, you roll it in, and you kind of just connect the top-level switches at each rack into a central switch, and voila, you have a cluster of a few thousand machines, and off you go. So if we fast forward a bit more, we're now building our own large-scale data centers because it doesn't make, we're now at this level, economies of scale make sense to build our own facilities. So we have about 20-ish of them around the world. I'll zoom in on one of them. We've also hired professional photographers. So this is our Oklahoma data center. You see that large warehouse-sized building down there. We're going to go inside and picture like a football field or two worth of computers in a really large building. This thing takes a lot of power. There's a lot of computational power there, though. So that's partly how your Google search returns quickly. We're searching, tens of billions of results of pages to find the results for you and collating them all. And the way we do that is we farm a single request out to, probably 5,000 or 10,000 computers and do a little bit of computation on each one. So that's another close-up. We leave covers off the front now. We've kind of gone back and forth over the years. You get better airflow this way because cooling these things is actually pretty challenging. Let's see. They look cool at night. You don't actually save any power by turning off the lights. It's all on the computers. Even the cooling infrastructure is pretty sophisticated. This is not actually just Google colors. It turns out these colors of pipes mean things to people who work on water-cooled systems. Red is hot. So you're all aware of this. Like the computer in your pocket, in your phone, is much, much more powerful than the computer on your desk 10 years ago. And Moore's law, which says that the number of transistors you can buy per dollar or pack on a single chip doubles about every 18 months. So this looks like a tremendous decrease, doesn't it? But the fact that it's a log scale is even more impressive, right? So that's a phenomenal increase in computing power per dollar over the years. And that's what's driving the ability to have lots and lots of computers that do much more powerful things than they were able to do 15, 20 years ago. And I'll point out that the price per bit of storage has dropped even faster than this. The problem is the fact that the price of storage has dropped has meant that data sets are growing even faster than computational power. So that's partly why we want these really large data centers that can apply lots of computation when you need it to dealing with different data sets. So these are some examples of data sets that Google has and that other people have as well. These are not small things. So over the years, we've taken that kind of pile of motley-looking computers and put together software on top of that that allows us to treat a bunch of separate computers more as a unified kind of processing system where you're less aware of the individual machine boundaries. So one of the first things we put together is, while we have thousands of computers in a data center, it'd be really nice to be able to treat their disks as like one big file system rather than individual machines, each with their own file system. So GFS was one of the first systems we put together that really tried to give us this illusion of a single large system. So what's happened with all these systems is that we've published a paper about how our system worked at a computer science research conference, and then some clever enterprising group of people get together and they decide they will create an open source variation of our system. We like to think our internal ones are a little better, but it's nice that the open source community has taken a lot of the techniques and things that we've been able to publish. For various reasons, it's hard for us to open source the code that actually runs our systems, but there are now open source equivalents for a lot of these things. So HDFS is kind of an existing open source distributed file system. In 2004, my colleague Sanjay Gemawat and I developed a system called MapReduce. And the realization for MapReduce is that a lot of computations you want to do on large data sets, they're actually conceptually incredibly simple, right? What you want to do is like count how many cases of cancer occurred in every county or something. And now you have 100 terabytes of data, say, and you need to process it. And that incredibly simple computation gets totally obscured by the fact that in order to run this computation in a reasonable amount of time, you need to do it on a lot of machines. And then you have this whole coordination mechanism to take the simple computation and spread it out over lots of machines, and what happens if one of them dies. So MapReduce is a framework that allows you to express a lot of kinds of computations in this very simple way, and then the underlying framework takes care of just magically making it run on thousands of computers and dealing with failures and scheduling the computation so that it's done efficiently. So it's a pretty useful tool, applicable to a lot of different things. There's an open source version called Hadoop. There's another one called MapR. And the next thing we decided we needed was a sort of higher level, more structured storage system, a little bit like a database, a little bit like a spreadsheet, but the spreadsheet kind of spans thousands of computers, and the rows have kind of an arbitrary set of columns that you can add to, and there's also a time dimension, so you can go back and look at how your data existed as of the beginning of 2015 or the beginning of 2014. So that was the next thing we decided we needed, and there's a couple of open source variants of that. The next thing we decided we needed was kind of like Bigtable, except instead of running in a single data center, it would run across all of our computers, or a lot of them, across all different data centers. And so you now have a distributed system that you can say, gee, I'd like this data set to be somewhere in Europe. And the system will now take care of saying, oh, gee, our Belgian data center is running out of disk storage, and let's move it over to our Munich data center and still allow people to access it. The other good thing that's happened is, as we've built up abstractions like this and open source sort of similar tools have been built up, there's now a bunch of companies providing cloud offerings that make the power of some of these kinds of systems available to external users who don't necessarily want to run their own data center and run their own open source variants of these systems. So a lot of the cloud systems that you see, these companies like Google, Amazon, and Microsoft are probably the three best known cloud providers, are offering the ability for them to run the computers that store your data and that run your computations. And that's a really nice property, because those companies can amortize the efforts of doing the management of all these machines across many, many different customers. And they'll be able to invest more in tools and sort of infrastructure that is useful across all those customers rather than across one. So that's why there's a big movement in all kinds of different businesses and organizations to move more of their data processing into the cloud. Okay, so some of the lessons that we've found at Google are that if you give people access to different data sets, obviously under the right access controls, but the ability to look across different kinds of data sets leads to kind of creative ways of using and combining those data sets. And if you don't have the ability to easily process, say, these three data sets because you think something interesting would come about by looking at joining this data, you have to go talk to someone to get access to one and someone else to get access to a different one. There's a lot of obstacles that sort of make it so that even interesting questions don't get asked. So you really want to unify all the different kinds of data you have in some system that anyone can sort of, with the right access controls, can go and access it and process it. And you want to make it easy and possible to do different kinds of analyses. So here's some questions I thought of. Is it easy for a single CDC researcher with the right access controls, obviously that's important, to easily analyze all data they have access to at CDC? Okay, so for example, all past outbreak investigations, those should be stored in a single centralized system and indexed and searchable, because if you're working on an outbreak investigation, it'd be nice to find similar outbreaks, right? You'd be able to see like what kinds of data they presented in their outbreak. Maybe you'd find ideas for things that are cropping up. All detailed case reports in every county and state. That would be incredibly useful. There's tricky privacy issues, which I'll talk about in the next slide, but that would be incredibly powerful from a scientific standpoint to be able to ask the right questions. All medical imaging data. That would be pretty powerful, especially if you could run some of the machine learning algorithms I'll talk about in a minute on those medical imaging data. How about the text of all the scientific and medical journals? That's pretty handy, right? Similar to why you'd want it for past outbreak investigation. So these are just the kinds of things you should be thinking about as you look to what capabilities you want in your data processing system, and in, even things that you don't think of as data, like textual write-ups of outbreak investigations, really are things that if you give people tools to search them and to manipulate them will be powerful. So, data privacy. I'm not going to touch on this too much. There are a lot of tricky issues with even things where you're computing aggregations across fairly raw forms of data. You're all familiar with the kind of like threshold level things you have to put in place to make sure that you can't identify individuals even from aggregated statistics. I think de-identification of raw data is kind of a nice partial solution to some of these issues, but there's a lot of issues around HIPAA compliance. I'm not going to address these in depth. I will just make one pointer that I think there are some algorithmic approaches you can use that you can keep raw data and have a filter on top. So there's a technique that was developed in 2006 called differential privacy. This was kind of a computer science, more of a theoretical research paper published at that time. The idea is essentially you keep raw data and you add a little bit of random noise to every observation, every time you process it. And the idea is the more noise you add, the harder it is to tell that an individual record is present or absent in a particular aggregation. And if you add a lot of noise, it's really hard to tell. If you add a little bit of noise, it's pretty hard to tell. And that's a knob you can turn. So the idea is you can give provable bounds on how likely it is that someone could reverse engineer that particular case is there. And you can say, I want to be, 0.00001 chance that I can reverse engineer that particular case is there. And I think that's the kind of thing that with some creative thinking of keeping raw data around, applying differential privacy filters, and allowing, say, anyone to process that raw data with a really high noise level, and having more stringent thresholds for what you want to do to get access with a lower noise threshold. Something like that could make sense. I'm not saying this is exactly the answer, but something like that I think would unlock the ability to do all kinds of interesting processing of raw data in a way that still preserves privacy. Okay, so the rest of the talk, I'm going to talk about a couple of kind of healthcare specific things that Google is doing that I think are kind of germane to some of the kinds of things people are doing, and then I'm going to switch gears a bit and talk about some of the recent advances in machine learning that I've been working on with a group of people at Google, and some of those things I think are applicable to various problems in healthcare. Okay, so genomics. The goal is to get you thinking about how these techniques might be applicable to problems in public health. Okay, remember the Moore's Law line? That's that one. This is the price of sequencing a single human's genome. The first one was pretty expensive, $100 million. Actually, it might have even been more than that. But it's dropped a lot, like way faster than Moore's Law. And there's a nice inflection point when different new technologies came online to make it even cheaper. So it looks likely that within a few years, you'll be able to do it for $1,000 a genome. And that means there's going to be a pretty big explosion in the amount of genetic data available. So Google, as a cloud platform, believes that genetics is an important enough sort of sub-vertical. In addition to producing general purpose kinds of services and tools, we should be building genetic-specific kinds of interfaces. So we have a genomics API. There's a bunch of information on those websites that is more tailored to the kinds of operations you want to do on genetics data. In particular, if you know something is genetics data, there are certain ways of transforming it and compressing it, because, after all, we're all 99.9% similar, or even 99% similar to mice or something. It's very compressible, let's just say that. And that allows you to take advantage of the fact that knowing it's genetic data, you can save a lot on your disk storage. And then you can do interesting analyses. So you can compute the principal components on this public 1,000 genomes data set. And the two principal components, if you look at it, you can't see the labels, but these are different kind of ethnic origins of people. I think the yellow is Asian, people of Asian origin. The blue is African origin, and some other ones in the center there. You see, these are very simple kinds of analyses to do, but 1,000 genomes is actually a fair amount of data. So you want tools that allow you to do this quickly. So we have a system that's kind of SQL-like. I don't intend you to read all this code, but this is now taking a bunch of genetic data and joining it with some annotations about which genetic positions are interesting. And we're going to pull out single nucleotide polymorphisms that are annotated as pathogenic in this data set, this annotation data set, and where the observed population frequency is less than 1%. So that's kind of the high-level thing you're trying to do. That's what you had to write to do that. And there you go. And the important thing to note is actually not the results, which are kind of interesting if you're into genetics, but the other thing to note is that, right? So in 22 seconds, you did that. And that's the kind of iteration speed that really makes it feel much more like a fluid interactive process. Like it's not like you had to go get lunch. It's not like you had to go home and then come back in the morning. It's not like you had to wait 2 weeks. You know, you got it in 22 seconds. And that's the benefit of using really large amounts of computational power applied at just the right moment you need it, right? Like I'm using this for 22 seconds, and then I'm not using the 10,000 computers or whatever, and someone else can use them. And that's the benefit of cloud services, because you can amortize the 10,000 machines not over just CDC people, but over, you know, thousands of other businesses. But you can burst to use this amount of computational power when you need it. And other people have done pretty interesting things in collaboration with kind of the initial alpha and beta releases of our API. There's an organization called Autism Speaks, which is focused on doing autism analysis. And they got the cover article in Nature Medicine doing a bunch of genetic analysis of their autism data set in the Google Cloud APIs. The other trend that I think is happening and will continue to happen more rapidly is there's more and more fine granularity health data available about individuals. In particular, like people keep fitness apps on their phone or on their Fitbit, and that's actually a pretty interesting window into the health of every patient. So I think there's a challenge, maybe more for healthcare organizations than for CDC, but how can you integrate that kind of information into giving patients advice or seeing how they're doing, like are they exercising regularly? Well, if you have access to their Fitbit logs, you can tell that pretty easily. One thing that we have a life sciences group of at Google that is interested in a whole variety of different life sciences projects. One thing that they're interested in is putting together a fairly large data set of very detailed data about people in the study. So about 10,000 people is the goal, where for every patient we have genetic information, we have epigenome information, we have transcriptome, we have standard lab tests at very regular intervals, and we have a bunch of survey data, we have medical health records. And the idea is, with that big a longitudinal study with very detailed information, we'll be able to see pre-disease and post-disease states for enough of the diseases that are common enough that you have them present in the longitudinal study. And so we think that's pretty exciting. It's actually a pretty big undertaking. So the place we're at now is doing the pilot study on a small number of people to just get the efficiency and the logistics of getting all the samples for this many people over time. Okay, so I think the future of healthcare is really going to be much more data-driven than it is today. The impetus for using genetic data, for using EMRs, health sensors, and all kinds of things is going to mean that we're going to use data and computation to help make decisions about patients much more than we do today. And I think there's a large opportunity to use this in a similar way to improve public health. And machine learning, I think, is going to be key to taking these fairly large, sometimes noisy data sets and building systems that can kind of do interesting things with them from the raw data. So now I'm going to shift to the machine learning part of the talk, which is what I've been really excited about in the last 3 years. So machine learning is often linked with artificial intelligence. You can think of artificial intelligence as the goal of making computers smart, and machine learning as being the part of computer science that it makes computers able to learn. And we're interested in this intersection of the two. And the observation is that it's actually pretty hard to program a computer to be clever than it is, and it's much easier sometimes to program a computer to learn to be clever by observing data and patterns, right? So if I told you to write a program in code to tell whether this is a giraffe or a cheetah, that would be hard, right? Given a bunch of pixels. But if you give it enough examples of things that are giraffes or cheetahs and let a machine learning algorithm process that, it can actually do it. And I'll show you a bunch of examples where that's the case. Relatively simple algorithms, large data sets, and the ability to build more and more interesting pattern recognition systems. And I think this is very amenable to a lot of healthcare problems, because a lot of the kinds of things you're trying to find are very subtle patterns that are often hard to discover. And often, if you have enough data, the computer is actually better at discovering subtle patterns than humans. Okay, so the particular kind of machine learning that is all the rage in computer science, this is seriously changing whole subfields of computer science and many other disciplines as well. They're not new. They were invented 25 years ago. They didn't work that well then because we didn't have enough computation and we didn't have enough big data sets that were interesting. So now we do, and they work fabulously well. So I'm going to go over what a neural net is. Basically, it's a system that can learn by example. So a really simple example is you have an email message, and you as a human, you mark that one as spam, and you read that one and say, that's not spam, and you mark this one as spam. Over time, you've built up a nice corpus of labeled data that says, this email message, spam, this one, not, and so on. And that's something you can use to train a neural net. So you give it an example input, and you have the desired output in your hand. You give it the email message the person read and marked as spam, and you say, this one should be spam. And this one, they didn't mark as spam, so it shouldn't be spam. So that's a supervised learning task where you actually have the desired output. And in a lot of cases for healthcare, because it's longitudinal, you can have pretty good large data sets that are a supervised setting. You have a bunch of people who got cancer, and you're now trying to be able to take a new person in their current state and predict, are they going to get cancer in the next 2 years? Okay, so one thing you can do is you can feed in pixels and try to predict a label. So that's a pretty complicated function, actually. So let me break it down a little bit. The way neural nets work is they're a collection of very simple trainable mathematical units. And they all collaborate to compute this really complicated function, where the function is, given pixels, output, cat or garbage truck or cheetah. So they're loosely inspired by what we know about how real brains work. They're not super accurate, and they're certainly not simulating things at like the biochemical level. They're kind of a very high-level abstraction where you take in inputs and you either fire or don't, as kind of the basic level of fidelity you're getting to real brains. But they are able to learn very complicated functions from data, and that's what you really care about when you're looking for subtle patterns. So think of it as something that takes something in one space and transforms it to another. And the fundamental building block is the artificial neuron. And this is where the analogy to real neurons is. The artificial neuron looks at a few inputs, in this case 3. A real one might look at 1,000 inputs in a real computer model. This is just computer software doing this calculation. So you take in some inputs. The inputs are floating point numbers, so they're just numbers. And you have weights on each of the inputs that say, how strongly do I trust this particular input? Or how much importance do I put in this input? And so those are those W values, W1, W2, W3. Those are just numbers as well. And so the whole thing is just doing a weighted dot product of W1, X1 plus W2, X2 plus W3, X3, and then applying some nonlinear function. So in this case, the nonlinear function is a really simple one. It's max of 0, x. Basically, no output at all, or output of 0, and then a linear output based on the weighted sum if it's above 0. So that's the fundamental building block, is one of these things. And the models we're training these days have maybe 10 million neurons in them. Your human brain has 100 billion neurons, so we're pretty far off. It's not necessarily a one-to-one mapping because they do different things. But your brain is pretty impressive. 100 billion neurons and 100 trillion connections. That is impressive. And from the age of 2 to 4, I heard that you grow 500,000 new connections per second for 2 years. That's just amazing. Anyway, so we don't have that many connections in our artificial models, but they can still do cool things. So the way you build a network is you essentially connect them, and you often do it in this layered form. So you start with some input data, and then you have a first layer of neurons that all get to look at the input data, and then you have another layer that builds on the outputs of that first layer of neurons. So you kind of propagate data up, and these neurons do their computation, their weights times their inputs, and decide what their output's going to be, and then you kind of work your way up. These ones now get to look at the outputs of the ones below, and you get your output. There you go. So the learning algorithm is conveniently simple. So X is your input, and Y is your desired output. So basically, it's the following loop. While you're not done, pick an input and a desired output. You run the network forward on that input and see if you get the desired output. If you do, you're done. If you don't, which is almost always the case, or often the case, you make little adjustments throughout the network to make it more likely that next time you see that input, you'll get that output. And it's just a repetitive process. You go over the training data, X, Y. You have millions of examples of X, Y. You just keep going over them, and you get better and better results generally until you reach the limits of your model has a certain amount of capacity in it. It can't remember anymore. It can't generalize any better. And the whole trick is not to necessarily make it remember a particular X, Y, right? You want to make it so that if you give me a completely different input it's never seen before, that it does a good job of predicting what Y should be for that example. Okay. And you modify the connection weights a little bit. Remember I said you make little adjustments? So it turns out that you can use the gradient of the error. So if you remember your derivatives, you're essentially trying to go to find a point where you're minimizing the error, and you just sort of make a linear approximation to where you are in the gradient, and you go down this. This is a two-dimensional gradient. The gradients we're actually dealing with are like 10 million dimensional, but don't worry about that. Just go downhill until you get to the bottom. Okay. So there's two properties of these kinds of models. One is when you have all these layers, all these weights are initialized totally randomly, by the way, when you're starting training a model. And all through the process of making these little teeny adjustments, they develop interesting pattern recognition capabilities. So the features are developed as part of that learning process, and they're also hierarchical. So if you look at a model that's going to take as input raw pixels, the very early features in this model, the ones at the lower layers, are going to be very primitive things like, does this little patch of the input have an edge at this orientation, or that orientation, or that orientation, or is it kind of mostly green at this little blob of pixels? And then the next level up is going to be more complicated things that are combinations of those things. Do I see a bunch of vertical lines in a slightly larger patch of the image, or is it got the kind of a weird speckledy pattern, or has it got nice curves to it? And then the higher level ones are actually very sensitive to very high level semantic concepts that you would recognize as a human, like is it a dog, or is it kind of a flower, or a bike from a head-on shot, right? So those are the kinds of high level features that these models develop, starting with raw pixels. Another important property, these things get better if you have more data and you can make your model bigger and you can afford to throw more computation at the problem. So you need to do all three of those. Doesn't do any good to do one or two, but if you can do all three, things just generally get better. And that's a really nice state to be in, because the bigger your data sets are and the more computation you can throw at it, you can use a really big model and get very, very good predictions. So here are some functions artificial neural nets can learn that might surprise you. Well, this one won't surprise you because I already told you that you can feed in pixels and get labels like that. So in the Android speech recognition system, when I speak to my phone, I say, Atlanta restaurants. We need to recognize the parts of those words and be able to break them into what are called phonemes, and then we have a language model that kind of tries to stitch a whole sequence of phoneme predictions into the fact that it's Atlanta restaurants. And we need to deal with all kinds of variations in accent and noise condition and things like that. But that's kind of a pretty complicated task. Neural nets are able to do that. You can give them a query and a document and predict the probability that the user will click on that document given that query. And you give it features of the query, like the words in the query, say, and the words in the title of the document, various things like that. This might be somewhat surprising. You know that statistical machine translation systems exist, so you can feed in a web page in Spanish, and those systems will output the page in English, say, or vice versa, English to French, say. But mostly those systems are composed of a bunch of statistical models that attack different pieces of that problem, and then a bunch of code to kind of glue all those things together. 3 people in my group published a paper in last year's NIPS conference, which is a big machine learning conference, on how to do this completely end-to-end with a neural net. So you essentially can feed in English one word at a time, and then you feed in a special end of English token, and then the model starts spitting out French for that sentence. So essentially in the representation of the model that it's built up at the point that it sees end of English, it's got enough representation power of that whole sentence, the meaning of that sentence, to be able to spit out the French equivalent. So that's a pretty powerful function. Remember, this is not like, f of x equals x squared. This is like f of English equals French. Another example using a similar kind of model, except instead of feeding your source language as English, you feed your source language as pixels. We can actually take in an image like that and generate a human-level sentence, like a close-up of a small child holding a stuffed animal. That's actually the output of the model on an image it's never seen before. So that's pretty good, right? That's an even more complicated function, maybe. So, complicated functions, able to learn them. And improvement is happening really rapidly in this field. The renaissance of neural nets is quick. So there's a big contest called ImageNet where you get about 2 million images and 1,000 different classes of images, categories of images, like cheetah or garbage truck or whatever. And you have to take in an image and produce the right label in the top 5 error. That's the metric they use for the contest. It's pretty hard. There's like 60 kinds of dogs in there. So it's not an easy task. The first time neural nets were used for this contest was done by 3 people who are now at Google, and they got a really impressive drop in error, 16.4% error. And then the next year, my summer intern, Matt Zieler, actually, who started a company, got 11.7%. And then the next year, a bunch of my colleagues decided to enter as an official Google entry, and they're at 6.7% error. Interestingly, there's a grad student named Andrei Karpathy at Stanford who helps administer and run the ImageNet Contest. So he decided in 2014 he would do the contest as a human. So the way he did this is he sat himself down with a bunch of training images, right? When you do machine learning, you usually split it into training data that the model gets to see, and then test data that the model hasn't seen beforehand, and then you see how accurate it is on the test data. So he split the training data into training data for him and then test data. And he actually did what a machine learning system would do. He got to look at these things and try to figure out how to recognize a Bavarian wolfhound from a schnauzer, from a garbage truck, from a windsurfer. And he actually put in, I think, 150 hours of training. And he got 5.1%. And he had a colleague try to do it, but they got frustrated and they only put in like 10 hours of training and got 12%. So he was pretty dedicated. This is a pretty good human. And so, you see that improvement in 2 or 3 years is pretty impressive. And then there was a paper from Baidu, which has a big machine learning group. They got 6%. So then Microsoft said, oh, we should probably publish a new paper. They get 4.9%. We said, oh, well, gosh, we don't want to be. So then the 2nd of March, we churned out our result. Actually, it's interesting in the machine learning community. It's pretty different than the other computer science communities I'm used to, where as soon as anyone gets a result, they just put the paper up on archive before it's even been accepted for publication. And so as soon as a conference submission deadline happens, not the conference acceptance notification, like all these papers go up on archive, and you can see what everyone's been doing. It like is really sped up innovation because ideas flow around much more quickly. Anyway, 25% to 4.8% in 4 years. That basically the message is computer vision now works, I think. And it really does work. You can feed in that thing, and, I'd say flower, but it can say hibiscus or dahlia. The training data represents like very different looking images, both as meals, so it's able to say, okay, that zoomed out view or the zoomed in thing, I'm still going to call it a meal. It makes mistakes, but they're kind of sensible. That is not a snake, it's a banana slug. You have to look closely to tell that's it's not a dog, but I had trouble telling if it's a goat or a donkey. And it may be one of each. I'm still not entirely sure. So we also have a lot of more specific visual tasks that we care about. We want to find text, for example, in images of the world, because we have all these cars driving around all the streets of the world, and we want to be able to read the names of all the businesses. So here's an example of an image. And this is one that we've actually annotated with the kinds of training data we want for a model to find text in an image. I hope you're all thinking of medical imagery at this point. So this is my favorite burrito place, actually, in Mountain View. And this is the kind of annotation we would do, draw boxes around all the text, all the legible text. And then we train a model. We just say, try to predict which pixels are text. And this is work that my summer intern and I did a couple years ago, and it works pretty well. The output of the model is basically pretty much on the text and pretty much not on anywhere else. There's actually text in the window that you maybe can't see. There's like a neon sign that's not turned on that it picked up some of, but not all of. It's actually pretty hard, right? Because there's all kinds of fonts and there's all kinds of different colors and orientations represented here, different sizes, because you're like zoomed in sometimes and far away from it other times. But that works pretty well. So I think there's a big opportunity here for training similar models on medical imaging data. And there's some people at Google who are interested in this as well. In particular, they're starting to work on retinal fundus images because they think that's pretty interesting, and they had access to a group that had 10,000 of them or something. There's some evidence they may show markers for other kinds of future conditions like Alzheimer's, Parkinson's, other kinds of things. It's certainly a strong indicator of diabetes, of diabetic retinopathy, and there's a lot of people even in the US that have this condition. So if you could detect interesting things from these retinal fundus images, that would be great. So they're building a tool. They've actually got a bunch of people annotating. They've actually got a bunch of images annotated, and they have pretty good initial results, but not good enough to put in this system. But it looks like it will totally work with thousands of images carefully annotated, which is a fair amount of effort, but not like a Herculean task. If you put like 5 retinal fundus experts on it, they could probably do it in a month or something. So that's great because this tool can be applicable to other kinds of imaging and signal types. The uses can be early detection, can be predicting the prognosis, therapy from prior examples, better alerts, just a real-time second opinion for any doctor. One of the things I think can be really beneficial for a lot of this machine learning stuff is one of the real bottlenecks in healthcare systems is doctor time, right? Like you just don't have enough doctors to look at all the data that you'd like to look at. But if you have the ability to have systems that can make predictions independent of a human actually looking at it, and they're pretty accurate, and they can, in the worst case, say, wow, you should really go see a doctor, but in other cases say, I'm reasonably sure this is all looking good. You could, for example, have someone take a cell phone picture of a skin lesion every day, and the model can sort of learn like what kinds of, is that serious or is it looking still pretty good? We have a bunch of people interested in drug discovery at Google. So there's a collaboration with Stanford where basically the task is given a small set of molecules with binding affinity to a target. You want to predict the binding affinity of new molecules. And that's a pretty important problem for drug discovery. And neural nets, which is the stuff in this paper, you don't have to understand all the results. The numbers in the bottom row are way bigger than the other ones, which is kind of nice. Okay, so let me shift gears a bit. So all the stuff I've been talking about so far is kind of perceptual data, vision, speech recognition kind of stuff. How do you deal with sparse data, which is often what we have? We have words, we have like disease name kinds of things. And we'd really like to be able to process that kind of data in neural nets as well. So the answer is this one trick called embeddings. We're going to represent every different vocabulary item, in this case words, by a 1,000-dimensional vector. So like just pick 1,000 numbers, and that's going to be our representation for a particular word. And we're going to have another word, and it's going to have a different 1,000 numbers. And the hope is that over time, as we train this model, we're going to learn that words that behave in similar ways are going to be close together in this really high-dimensional space. So in this 1,000-dimensional space, porpoise and dolphin will have a small distance between those vectors, and words that are not similar, like, say, camera and porpoise, will be pretty far apart, and Paris. You'd like to say porpoise and dolphin share the same sense of porpoise. Maybe not. Okay. Okay, so how do we learn these? So a very simple model developed by my colleague Tomasz Mikolov primarily, and some others of us, is you take a small window of text, so you can start with like the raw Wikipedia articles, and you pick a 20-word window, you pick the center word, in this case Obama, and you pick a nearby word. And you say, I'm going to look up the 1,000-dimensional representation for Obama, and then I'm going to try to predict the other word that I've drawn a box around. So I'm going to use the representation for Obama to try to predict the word Putin. And if I'm able to do that, great. If not, I get little adjustments I can make to my prediction module, and then little adjustments I can make to the position of the word Obama to make it that I'm more likely to predict Putin and maybe other world leaders when I see the word Obama. And this actually works really well. So if you look at this model trained on Wikipedia data, I'll show you 3 words or short phrases. Tiger, shark, these are the nearest neighbors to the word, vocabulary item tiger, shark. And you can see they're all quite closely related to tiger, shark. If you look at car, you see cars as the nearest word to car. But you also see other things like synonyms, like automobile, autocar, pickup truck. It's really understanding the concept of car. It's not treating it as a sort of unknowable token CAR. It actually knows about cars. And that's pretty powerful for doing information retrieval or like text understanding. Here's a kind of model we use a lot. We have these different kinds of embeddings for different kinds of pieces of the input. So the idea is we want to predict the probability that a user is going to click on some bit of textual content. This could be a search result. It could be like a result article in a social stream. And we have the words in the query. We have the words in the text. We have the user's country. We have a bunch of other features. So we just put those through embeddings. And so now we have a whole bunch of high-dimensional vectors. We just concatenate them all. And now that's our input to the rest of our neural network. We feed that through, and then we do logistic regression on the top-level features of those final layers neurons. And we try to predict, is it likely you're going to click on that? We have tons of labeled data because we've shown lots of text to lots of users, and they've either clicked or not clicked. So I'm going to change this. Look how little this changes except for the word epidemics. Right? You want to predict, is someone going to be sick, given a bunch of factors at the bottom. And typically you might use logistic regression on the raw features. But these embedding models actually are very powerful because they allow you to smooth things where you don't have very much data. And say, like if you think about the word autocar, I have very few observations of the word autocar, but I have a lot of car and cars. And so by making it so that you can be in the space of cars instead of at exactly the hard symbol autocar, I can now take advantage of all the statistical power that I can get from starting with cariness rather than starting with autocar. And that's a pretty powerful thing for these models. That's partly why these models are doing way better than just simple logistic regression models. We have one more technique I'm going to talk about, paragraph vectors. So the idea here is you want to embed longer bits of text rather than just individual words. So I'd like to have an embedding representation so that if two paragraphs are very similar, then the representation for those paragraphs, which is going to be a high-dimensional vector, is such that those high-dimensional vectors are near each other. So I'm not going to talk about how to train that model. There's a paper you can look at there, but it's not too complicated. There's an important note. Paragraph vectors don't have to be paragraphs. They could be things like sentences. They could be a whole document. They could be a user or a product, or perhaps germane here, different epidemics or hospitals or counties or populations. So I think this can be applicable to a lot of different kinds of things where you're essentially trying to cluster these kind of large nebulous things. And so I'll show you how well this works. So we trained paragraph vectors so that we have a paragraph vector based on the article text of each Wikipedia article. So now I have a 300-dimensional vector that represents what my summary of all the words in that article is. And I can look at the nearest neighbors for the article on machine learning. LDA is a different technique for doing kind of document clustering, and paragraph vectors is on the right. And they're both pretty good, but there's a bunch of kind of weird things in the LDA list that don't really make any sense. And the paragraph vectors topics are all spot on. And if you visualize these high-dimensional spaces, so this is one dot for every Wikipedia article, or for a sample of like 50,000 of them or something. You can see Wikipedia has like these higher level categories, like this is an article about sports, or this is an article about music. And you can see that, for example, all the music articles are very close together in this high-dimensional space. And all the different sports, like actually each one of these little subclusters there is for a different sport. And you see things like films and music, actors are kind of between the two because often there's a lot of crossover people who are kind of music-y, filmy people. And then over on the other side of the world, you see things like computer science and mathematics and biology and proteins. And those cluster nicely as well. So imagine if these were epidemics or epidemic write-ups. So now you would have the ability to find very similar epidemics to the one you're currently looking at. Right? I think that would be a pretty powerful kind of way of looking at textual data in a way that's useful for people and allows them to retrieve things in a way you can't quite express. Like you want to express, I want an epidemic kind of like mine, but that's a really hard query to do with kind of Boolean search terms. But with these paragraph vectors, it's very easy. You can have an interactive browser that would let you view like the nearest 10 epidemics and just kind of look at them. So I haven't talked about a lot of direct public health applications, but these broad set of problems we've applied deep neural nets to, I hope convince you that there's a lot of applicability to all kinds of healthcare problems. We've done it for everything for image recognition and speech, kind of more perceptually things, to language understanding, machine translation, advertising, drug discovery, you name it. We have about 100 different teams at Google using deep learning, and we've launched 50 production services that all use neural nets in various ways. So this is the future of machine learning, and it's going to be pretty powerful for dealing with complicated patterns emerging from big data sets. So, back to where I started. The first thing you need, though, is the ability to get all the data you have together in a way that it can be conveniently processed. And then, once you've done that, you can start using simple tools that you already use, but on lots of joined pieces of data. Like all the data at CDC should be accessible to anyone, and if you can do a query on any public data set at CDC, or all public data sets at CDC within a minute, that would be a really powerful thing, I think, because it really does change the pace of scientific exploration to answer questions in a minute rather than months, right? That's just a fundamental difference in pace and cadence. And you need appropriate tools to be able to process them. The second part of the talk was about deep neural nets, which I'm excited about. They work really well across a wide variety of domains. They're going to be powerful for all kinds of health problems, public health ones, healthcare setting kinds of ones. And some more info. I think there are cloud services and or open source tools. So you can make a decision, do you want to run your own service? Do you want to use cloud tools that will enable you to deal with large data sets? Remember the power of what I showed you where you get the results in 22 seconds? That's because you're doing that computation on thousands of machines. And that really makes that kind of instant interactive feel to doing research. There's a bunch of excellent machine learning courses. I think one of the things that's happening across all sciences is that people realize that it's very important to be able to do some sort of predictive modeling of their data as scientists who are not necessarily computer scientists. And I think there's enough tools available that are pretty high level that general scientists are picking up these tools and using them in their day-to-day work without necessarily having to partner with someone who programs. And I think that's a good goal, because anytime you sort of say, oh, I have this great question I want to ask, and gosh, I just can't find anyone to implement it for me. You really want the tools to be high enough level that people can sort of fish on their own, I guess is a good way of saying it. There's a bunch of open source packages for deep neural nets, if you think those are interesting, that work well for moderate data set sizes, Theano, Torch, and Caffe. There's a bunch of papers and references to things I've talked about on my website, and I'll take questions. Oh, okay. Sure.
Thanks very much. That's really terrific. And for many of us in public health, EpiInfo formed how we think about public health issues. It wasn't just a tool. It was a way of structuring our thinking. And one of the reasons I'm so grateful that Jeff has come here and spent time with us is that we may need to begin thinking in very different ways. So to help us there, I'm going to start us off with a question. Okay. Can you help us understand and apply to public health what a 1,000-dimensional vector means?
Sure. So the 1,000 is kind of arbitrary. You just want enough sort of space in some high-dimensional space that you can represent interesting relationships. And the way I would characterize it is, suppose each vector is a disease. And I have some very common diseases, and I have some rare diseases. And I have some observations of each, not very many for the rare one. But it looks like the rare one kind of behaves in similar ways to this more common one, or is kind of like this common one and kind of like this common one. So you would want the representation for that rare one to be between these two, because it's a little bit like this, a little bit like that. And I think that's the real power, is this ability to kind of smooth and generalize from cases where you have very little data and can make up valid, reasonable predictions based on the limited observations you have of that rare disease by taking what you know about other things around it that seem similar.
We have some time for questions. We'll start here at the left-hand microphone, please. Please identify yourself.
Paula Braun, entrepreneur in residence here at the CDC. And I'm working on an interesting project to modernize the way that mortality reporting happens here in the United States. And one thing that's challenging about that is, particularly for cause of death, you're trying to take physicians to think about all of the circumstances that were present at death and determine the etiology and what was the causal sequence. And so I was wondering the extent to which neural networks could potentially be used to allow a physician to talk through those conditions in natural language, and then it could parse out the medically relevant pieces of it, and then help determine perhaps like a causal sequence, maybe using something like a Markov chain or other advanced techniques.
Yeah, I think that kind of thing is entirely possible. So the question is...
to what extent has Google looked into this type of...
so we haven't attacked that particular problem because it's a little bit specific. But in general, I think you want to make the problem as simple as you can. So I would kind of divorce the speech recognition aspect of it from the making a prediction from these sets of things. But I do think a model where you looked at the patient's medical records or whatever's available to the doctor, plus maybe a few thoughts the doctor jots down as text, you could make a plausible prediction of what you think the likely cause of death is. The trick will be if you want that last little bit of the text the doctor enters to be part of the input, you're going to need a bunch of example data where you've labeled, you actually have that text and the actual cause of death.
What would the n size need to be to do a prediction, would you estimate? Hard
to say. There are probably like only 10 or 20 causes of death generally, maybe at 50, I don't know.
There are a lot more than that.
Really? I'm thinking like illness or like hit by car. Maybe you want more granular ones.
Thank you.
Yeah, so the more fine-grained you want to be, the more data you need probably.
Hi, my name is Liz Kurlikal. I'm the incoming EIS class. I was wondering if you could talk a little bit more about some of the limitations or challenges when you have sparse data input, so a very rare disease or a new emerging disease, and how you could use this system in that situation.
Sure. So, I think one of the strengths of these embedding models is that they actually deal pretty well with rarer data and more common data. If you think about query words, we have some query words that are issued, all the time, restaurants or something. And then we have some very, very rare query words that are not issued very often. And that's pretty similar to the situation where you have some very rare diseases that you hardly have any observations for, but you know that they have similar kinds of symptoms because you're using embeddings for everything, and you can realize that they're behaving in a similar way to this other kinds of things where you have more data.
Thomas Cook, Mercyhurst University. I just first wanted to mention I have at least one project that is using EpiInfo 6 with the year 2000 patch on it, so thank you for creating that. But the question is, so there's a lot of promise with big data, particularly linking healthcare data together, but could this machine learning be used on the statistical programming side to start to check for errors in coding and things like that? Because there's a lot of human errors that are made in doing research that could possibly be detected through simple recognition of patterns in code and so on that's faulty. Because I always tell students that EpiInfo is stupid or SAS is stupid. It'll do whatever you can do. Could you come up with a way to foolproof some of the
Right. So the former one is very similar to a bunch of kinds of security detection things you want to do on code. You want to inspect it. Will I have a buffer overflow? And that kind of thing. And there are some people at Google looking at using it in that setting, and it sounds pretty similar. The second one is kind of like the translation problem, right? And if you have enough aligned text where you have a bit in one programming language and the corresponding bit in another programming language, you could probably learn a translation model that would not be 100% accurate, but would kind of get you most of the way. So that's the problem with neural nets, is they're applicable to so many things. You have to kind of pick and choose. We've kind of, within our group, picked problems we think are really, really difficult and challenging, and we've worked with other teams at Google kind of in a more consulting role for problems that are a little more niche and are important to that team, but not necessarily as central. And then we have other teams that are using our stuff without really even talking to us because we have enough documentation around our software that they can just pick it up and do it. I don't think we'll work on that particular problem because it's more in the niche category. I do think it would be useful, and I do think you could make a fair amount of headway just picking up one of the open source packages and trying to collect a data set of interesting ways of expressing, say, R and SPSS or SAS or something, or I don't know what, something like that.
Hi, thank you for the talk. Arthur Wendell, Healthy Community Design Initiative, National Center for Environmental Health. We deal with how transportation systems impact public health. One of my questions is about how well the classification system can be communicated. So it sounds like the error rate changes over time. And that's one of the particular challenges as things learn. It's great that it's improving, but how do we learn about that, or how do we get a handle on that as public health practitioners in order to bring it into our understanding? I have a mobile application that can tell whether I'm biking, walking, or running.
Right.
I think it's awesome when I'm riding my bike and it classifies me as driving in a car. But I'd like to get a handle on trying to figure out how that classification changes, how those classification changes can be brought about for public health.
Right. So I think this is one sort of pretty common argument against neural nets versus other kinds of machine learning where the model is fairly opaque in neural nets. You feed in some inputs and you get some output, and it's not exactly clear why you get this output. Partly, I think there's two answers to this. One is if the model is much better at predicting, then for a lot of problems, you don't necessarily care about understanding why it predicted something if it's just much better than something that is less accurate but more understandable. And we've actually have a lot of groups at Google that want more understandable machine learning methods that have been sort of won over by the fact that these things just work way better for their problems. And so they said, okay, I guess we don't care that much. But the second thing I'll say is I do think there are ways to make these systems more understandable. We have a bunch of tools that allow us to visualize kind of what is happening for a neural net when it makes a particular prediction on a particular example, and understanding, which neurons are firing and why, and looking at that at different levels. So in part, I think it's a bit of a tooling and sort of visualization kind of problem that we have tackled somewhat, but can definitely do more. A good analogy someone made is a neural net is kind of like being a neuroscientist, except the precision of the measurements you can make is infinite. Like you can basically go in and measure anything. And so if you think about it from the perspective of a neuroscientist trying to understand a complicated neural system, but with the ability to insert probes anywhere, that might be kind of a good way of figuring out what kinds of things you would want to measure and understand.
I think we have time for one more question.
Bob Chen, EIS 84. Many of the issues in using healthcare data does relate to privacy. And for the foreseeable future, much of the data is structured at the individual patient level. And we have been able to overcome many of the issues related to privacy by developing the distributed data model, where the individual HMOs or managed care keep their own data sets, but by creating a data dictionary ahead of time that then allow one to send query codes across the different managed care organizations and then return the results, and then you're able to kind of aggregate that. And that model is now being used by FDA and a whole bunch of other folks for their large data sets. And that may be something that, for folks in the audience, that some of what you described is actually very sci-fi wise, but this is an approach that would be more accessible to what they're working on at this point.
Right. So I totally agree that the distributed model makes a lot of sense if there's not other ways to deal with the privacy issues. And I think it's worth looking at things like differential privacy and having the ability, because the problem with that is you can't then join that HMO's data with anything else if you only get back aggregate results from that query, right? And often I think you'll find questions you would want to ask that would be more powerfully answered by being able to look at more data in aggregate. Do machine learning, say, on a bunch of different HMOs, medical records data, for example, right? That would not be possible in the distributed model, but might be possible in a differential privacy kind of filtered way. But I agree it's a really tough nut to crack, but I think the benefits to public health of solving that will be very large. So it's worth thinking about at least.
Please join me in thanking Dr. Dean for his presentation.